Centennial and Jubilee Alumni Lecture this semester. This is a special lecture series that we have in celebration of our Centennial and Jubilee for the department. And the idea of these seminars is to bring some of the younger alums of the department that are distinguishing themselves in academia and in industry in various ways, and give you an opportunity to see that the legacy of the department continues and that there's a young generation of emerging leaders in chemical engineering and material science. So it's a great pleasure to introduce today's speaker in this series, Micheal Baldea. He's a professor in the Department of Chemical Engineering at the University of Texas at Austin. I know Micheal for a very long time. He applied here to graduate school in 2001 after graduating from the Department of Chemical Engineering at Cluj-Napoca University in Romania. I was a director of graduate studies at the time, and he was the last student that I admitted. After a lot of hesitation and a lot of research, many phone calls, we had no experience with Cluj-Napoca up until that time. And I very quickly realized how good of a decision that was. I was very lucky. He joined my group. He did a terrific PhD thesis. He graduated in 2006, and he joined Praxair. About 6 months after he joined Praxair, he called me desperate. He was enjoying the industrial experience, but at the same time, he was missing the academic experience. And after a couple of years, his dream became true. He joined the chemical engineering department at the University of Texas at Austin, a department with a long tradition of excellence in process control. He's done a terrific job since then. He has developed a multi-dimensional research program, lots of collaborations with industry, a mix of fundamental and practical problems. He's been recognized with a number of awards, for example, the CAS Division's award for outstanding young researchers, and also an AICHC Institute award for excellence in industrial gases technology. So it's a great pleasure to have Micheal back today. The floor is yours.
All right. Thank you. Thank you for the kind introduction and for the invitation. I'm deeply, deeply honored to be here, honored and humbled to be back and see what the department has become. It was excellent in the day, and if I could say, it's more excellent now. I will say that it feels weird to be on this side of B75, so I took a lot of classes sitting on that side. I usually tend to sit towards the back, so it's okay. And it's a pleasure. It's a pleasure to be here. And I will say this invitation really sent me down the memory lane a little bit. So some nostalgia when I got it, and made me think of what we did back then. This is 16 years ago. It was a very nice group and a very intellectually stimulating group that we had. So a lot of work, but a lot of fun. So this is at the Dautides family home. We did a lot of globe-trotting travel. This was back in Romania, 15 years almost to the day. And I'm happy to report that Professor Dautides hasn't aged a single bit. Inside too. Inside too. So this was 15 years ago. This was the first decade of the new century, the new millennium. We're now in the third decade. And we're facing probably different problems that we were facing back then. Maybe not as different, but certainly more acute. So what I will talk about today is how systems engineering can and should be considered as one of the tools to take care of pressing issues that we as a planet are facing. And the United Nations took care of trying to set the framework for us, trying to define what what the problems are. And obviously, as you'd expect, at the top of the list are energy, climate change, and then food and water. And the term, this nexus of food, energy, water has been coined, and is something that a lot of people are looking into. But what I want to talk about today is how and why these are chemical engineering challenges. So why are they chemical engineering challenges? If we look at this picture, these are data from the Energy Information Administration. And the picture that we see here is that the chemical industry, at least in the United States, the chemical industry is a huge player in the energy field. So this shows the percentage or distribution of energy consumption in industry. And you see here that chemical and refining, which I argue is also chemical production, makes up for a good chunk of that. Okay, so we're looking at close to 50%. So energy use and then carbon or greenhouse gas emissions, we're high up there, right, and growing. So the chemical industry is a huge factor in this landscape, this picture. And the natural question is, so we at the undergrad level, we teach process design, and it's a natural question to ask, well, can we design a new chemical industry that would be greener, more energy efficient, less impactful from an environmental point of view? And if you look at the literature, there's any slew of papers you can go through, and it would seem that, yes, we can. So we can turn biomass into fuels. We can make plastics out of renewable things and so on. And so I think looking through all this, I think the answer in Minnesota style is you betcha, right? We can design a new industry. I think that's not the main question. But I think the critical look at this literature and these results is that these studies tend to minimize, and again, we go back to our process design class real quick, they try to minimize the per unit costs. And we think back of basic things in our curriculum, and we say, well, that means we have to have larger and larger plants, right? So your economy of scale should kick in, and the bigger the plant you make, the cheaper the product per unit is going to be. The problem with that is a large-scale plant, a world-scale plant that would utilize some renewable things to make useful products is going to cost billions. So even the largest chemical company can't afford to do that. They can maybe afford one project like that at once, right? And they're really betting the farm. Two of them, if both of them fail, they're out of business. So essentially what this is telling us is that you might actually have to buy a new car to improve your gas mileage and so on. So the question is that really what we want to do? And your grandma would be telling you that, well, maybe you can change the way you drive your existing car in order to improve your fuel economy. So the realistic alternative to our current energy problems in the here and now is to look at how we can utilize existing assets, existing plants, in a way that's adapted to the current context, to the current energy landscape. So the question I'm going to ask today is, how do we adapt the operation of existing assets to the current context? So just to give you some background as to what I'm referring to, what exactly does it mean that we operate the chemical plant? So if we have a physical facility, there are several layers of decisions that have to be made in the process of its operation. And these decisions go in a hierarchy. We start with what's called production management, and simply put, that's what to make, when to make it, and what quantity, such that we meet market demand and maximize profit. And here, the main assumption is that we are operating at the steady state, so we have this facility, it will run for a while, it will make the same thing, then we switch to a different thing, and so on. Right. Control is more in the here and now. By the way, these decisions are made over a long time horizon, so these are business decisions. And then in the here and now, we have control. So control is based on measuring current conditions, making decisions on that basis. This is done in real time, it's done online, and it accounts for the dynamics of the process. Here, since we're assuming everything is at steady state, we don't count the dynamics of the process explicitly, at least. Right, so here we have a hierarchy of decisions. This is how it's been done top down. So whoever was in production management, the business entity would tell plant operators who were in charge of the control system what to do, and there was not much feedback going on in the other direction. So naturally, when we started looking at this problem, we asked ourselves, is this established paradigm, by the way, this is adapted, just made prettier from the textbook that you guys are using here for control. So we asked ourselves, is this paradigm still true in today's world? So let's challenge these assumptions. First of all, we said chemical plants are thought to operate predominantly at steady state. So if I look at this picture, this tells me these are electricity prices in Texas on a given day. And you can see here that electricity prices go up by about a factor of 20 during the day, right? The electricity market is now free, deregulated, so you can have these fluctuations. And those are obviously driven by demand. So people get home at 5 p.m. and turn on the air conditioners and so on. So demand is going to be high on the grid at that point, and it's low early in the morning. Right? They're also driven by the fact that now there's there can be up to 50% renewables on the grid. So wind blows harder early in the morning, so there's excessive electricity at this point. So electricity prices can actually go negative in real time, but this is desynchronized from demand. So all the point of this, of showing you these data, is that market conditions today are different from what they were. And market conditions today are highly, highly variable. So if you're the operator of a chemical plant that uses electricity, well, then you have to think of an operating strategy that can ride out that peak price and take advantage of the lows. So you can think of an operating strategy where you up production when prices are low, so electricity is cheap, store whatever material you made in excess, and then when the prices of electricity go up, you would want to drop production, lower your energy or your power draw from the grid, and use the stored material to meet demand at this point. So, of course, this strategy now requires very frequent changes in production rates. So you're no longer operating at a steady level, but you'll be going up and down quite a bit, right? So I will say this first initial fundamental assumption is that a chemical plant will be spending most of the time operating, kind of coasting along a steady state. I will submit that that's false in today's context. We also assume oftentimes when business entities make their calculations, they often assume that switching from one operating state to another, from one product to another, takes a lot less time than you spend operating at that steady state. Right? So these transitions can be done quickly or the time is negligible. So is that true? Let's look at the other side of the equation, across the fence at a chemical plant that uses electricity. Again, I'm going to use this example of electricity since that's one of the most dynamic markets that we're facing today. So if I look at this chemical plant, it's an air separation plant. That's kind of the system that I spent a lot of time with in industry. The way it works, we'll go into more detail later, but in principle, it's a cryogenic distillation of air. So you have to compress, liquefy an airstream, and then you have to distill it. And you make nitrogen here, gas nitrogen. The main thing here is that the compression is driven by electric motors, and the consumption of electricity by those motors is quite high. So this plant is essentially just an electricity user. Air is still free. The only thing they pay for is electricity. So if I wanted to use this plant to do what I said before, meaning increase and decrease production to track electricity prices, then what I would have to do is decide at what level I produce nitrogen. If I make liquefied nitrogen or gas, liquid can be stored, by the way, very easily. And I probably have to do that over every hour that the electricity prices change. So this plant can play nicely in the sense that production, these are industrial data, by the way, production rates can go up and down, so I can very easily alter my electricity consumption. The problem is the product that I'm making is a very high purity stream. So there are plants that make nitrogen with parts per million oxygen. There are plants that serve the electronics industry that make products with part per billion concentration, right? So very, very sensitive to any changes in operation. And as it turns out, for this plant that's operated properly, the level of oxygen, the impurity level, can change over a course of a couple of hours. So even after I made one change in the production rate. So what that means is that I cannot possibly assume that this transition time between operating states is negligible. On the contrary, it's about on the same time scale as the changes in production. And also run the risk of exceeding some impurity limits, which would lead to severe contract penalties. So again, if we are to track electricity prices that change on an hourly basis, I have to account for the fact that the dominant time constant, or the time the system responds, is also in the order of hours. Which means that I cannot assume anymore that transitions cannot be or are negligible. So I have to account for these explicitly when I plan and schedule my production. And finally, we said market conditions. Back in the day, you could plan on some well-known electricity prices, feedstock prices, and so on, so we can assume that these are known or can be forecast accurately. Well, let's look at electricity prices over a longer time period. And there are two markets here. There's the day-ahead market, so something that you can count on to know every day at 3 o'clock. And then there's the 15-minute market, which is cleared 45 minutes before the prices come into effect. Right? Can you forecast this? If you can, you're going to be an instant millionaire. You can't. So you can know, you can see some periodicity, but certainly being able to predict these ginormous peaks in the 15-minute market is impossible, right? You can prepare for them to some extent, but you don't know. So market conditions are capricious, and an air separation unit, if we were to refer back to our example, is usually treated by its customers as a utility. So they expect to open the valve and oxygen or nitrogen will flow, right? They don't care when and how that's produced. It just has to be there, just like water or electricity. So I would give this one a partially true, so it's not quite a Pinocchio, but it's there. And that means that market conditions are difficult. So we live now as an industry, as a chemical industry, we live in a highly variable environment. And that is what I am trying to define and deal with in the next part of this presentation. So, which takes us to what production planning and production scheduling, so what to make, when, and how much, what the framework for planning and scheduling should look like under these circumstances. So what I will argue today is that this framework needs to be fast. So we need to be able to compute new solutions as new information becomes available or circumstances change. We need to be detailed. So we have to have an unprecedented insight in the actual behavior of a facility. We need to understand its dynamics and can account for them when we think of making business decisions, which we haven't before. And finally, I will also argue we have to be recursive, meaning that solutions have to be updated as soon as new information becomes available. So what does a scheduling problem look like? It's an optimization problem, and I will use for now what I called word equations. So I'm going to try not to use a whole lot of math for now, and describe this problem really quickly. So what I'm trying to do here is to minimize the total cost over some time horizon in the future. And that total cost is a function of the power draw at any time instant and the price at that time instant. So I'm integrating that over time. There's some constraints here that say I can only make changes every hour in my production targets. And then I'm also incorporating a very detailed first principles model of this plant. So we were able, after about a year and the master's thesis, to develop an accurate dynamic model of an air separation plant. And we said we're going to use it to decide super accurately what the production schedule should look like in the presence of varying electricity prices. So what does the solution look like? Ignore this part for now. I'll explain that later. But let's start from here. So these are electricity prices. They're real electricity prices for 3 days. And you can see there's a little bit of peak in the morning and the big peak in the afternoon. These are generally ascribed to retail or consumer level residential use of electricity. And you can see that the production schedule, so this means the production rate and the associated power draw, are exactly in anti-phase with electricity prices. So what this means is I'm going to make more nitrogen, liquefy it, store it in a tank, drop production when electricity prices are higher, and then really drop production when I hit these peaks in electricity price, and use nitrogen stored in the tank to satisfy demand. Right? So why is this important from an environmental point of view? It's important because this is when renewable electricity generation is high. This time here is when generally fossil fuel peaker plants are brought online to meet demand. So this is when emissions are high. This is when emissions are generally low. So indirectly, this is not entirely altruistic. So we take advantage of lower prices, but indirectly we are helping the cause of lowering the emissions associated with the industry. Now, the old car analogy here is we're changing our commute schedule, right, to avoid rush hour, and that's exactly what we're doing, right? We make more stuff when prices are low and there's no congestion on the grid. Then we also buy fuel where it's cheap and store it in the tank. So by changing our driving pattern with this analogy, we are actually improving profitability for the plant, and we're also helping the environment. Now, what does this amount to in numbers? This is a small plant, so it costs about $1,000 to run for 3 days. It's not a whole lot of money. But compared to constant production rate operation, we're saving 1.2%. And these are numbers that were verified with industry. So is that a lot? It is a lot, because in an industry that's more than 100 years old, you can imagine they squeezed about everything they can out of their facilities. And now if you can come in and say, hey, with no capital investment, just a change in your operating strategy, I can give you 1.2% savings, that is huge. The problem with this solution was that we looked at 72 hours ahead in time. It took us 100 plus hours to solve this problem initially. So I went to our student and I said, well, is this really important practically? And the answer is, of course not, right? You can't expect that this will be useful. The time has passed, right? The ship has sailed. You need a much faster solution for this class of problems. This is a dynamic optimization. These problems are generally known to be challenging to solve, especially because of the size of this model. This model ended up having around 5,000 equations. It was highly nonlinear and difficult to deal with. So our next challenge was to say, well, if we really want to do this, we have to come up with something that's fast. And the main observation here was empirical initially, and it goes back to the time when I was doing my thesis at Minnesota. And the observation was that chemical plants generally have a few dominant dynamic modes that are pretty slow. And those are small in number compared to the general size of the model of a chemical plant. Also, combined with the observation that not all the variables that you can measure in a chemical plant are relevant to production scheduling. So you would care about production rate and product quality, but you may not care about the temperature at the bottom of the distillation column and so on. So what that tells us is that we can, and we should, use a lower dimensional dynamic model. We also notice here that what scheduling here sees is sort of the ensemble of the chemical plant and its control system. So we might, again, not care in great detail about what these data or this information exchange is. We just need to model this ensemble. Right, so this lower dimensional model can capture what we call the closed loop dynamics of the plant, the dynamics of the plant and its controller. So this is why we came up with this concept of a scale bridging model. It's a low dimensional model that captures the input-output behavior of a plant, meaning that it will tell us what the scheduling relevant outputs do when we change targets, production targets at the scheduling level. So that includes the process and its controller, and that this model can be embedded in a scheduling calculation. And scale bridging meaning that it bridges the time scales between the fast or relatively fast dynamics of the process and the longer time horizon that we consider when we do production scheduling. So going back to our air separation plant, well, what are these scheduling relevant variables? And again, we did this empirically initially. Later, we were able to come up with a data-driven approach to actually automatically determine what these are. But we looked at what are they? Well, it's the production rate and the power consumption of the compressor. There's a liquefier here to store liquid nitrogen. There's a temperature driving force here in the condenser of the column. There's some holdup in the reboiler condenser, sorry. And then there were a number of temperature constraints around here that were mostly related to safety. And then finally, we had a tank capacity constraint. So you can't overfill it and you can't drain it all the way down. Right, so that's it. Out of the 4,000 odd variables, this was all we needed. And we were able then to learn from operating data, we were able to learn how to model these variables. And we chose a model structure which turned out to be hugely consequential. You can do it in any way possible. There's many ways to learn dynamic models, etc. Why we chose this Hammerstein-Wiener structure, which consists of a linear state space dynamic model flanked by two static, so not time-dependent nonlinearities, is this allowed us, first of all, we were lazy, so there's already a good set of tools available to identify these models, so that cut the time. But as it turns out, these models then give rise to a very interesting problem structure for the scheduling problem. So they can be, this was Morgan Kelly's realization that these models can be, under specific circumstance, can be linearized exactly. So now you've turned a nonlinear problem into a mixed integer linear problem. And then further, that problem has this incredible structure that lends itself to a Lagrange relaxation approach. So without going through the details of how that's done, I can show you the progression of the solution time after applying these successive techniques, right? So first we started with the full order model. So we used the dynamic model that was derived of the first principles. We said 100 plus hours of CPU time. We used the Hammerstein-Wiener models by themselves. That cut it down by a factor of 20. And really the results were ostensibly the same. We then formulated this as a mixed integer linear program by using our linearization techniques. Well, that cut it down to 12 minutes. Then with the Lagrange relaxation, we cut it down to 7 minutes with really very little change in the value of the solution. So the main thing here was by understanding economics, scheduling, dynamics, physics together, we were able to devise a strategy for reducing the solution time of a very interesting and important problem by orders of magnitude and without any real penalty in the results. So what does the schedule look like now? Well, that's why I'm showing these different strategies. You can see the schedule are essentially the same. The reference point being this constant steady state operation. So you can see overall there's a penalty to be paid by playing the market, and that penalty comes in the form of increased energy use. So liquefaction is not free, right? You have to remove that latent heat, and that to the tune of about 3% increase in energy use. But this energy use is maximized at off-peak hours when wind generation is very high to the point where they have to curtail wind generation. We use nitrogen liquefaction as a means for energy storage. So we are, instead of using a battery at the grid level, you're storing energy in the form of molecules, which is cheap, right? Grid level batteries are expensive. The other benefit of this strategy is that peak power is reduced. So when demand on the grid is really high, we're actually low. And then the power consumption is in line with whatever you'd pay today in terms of making nitrogen. So, of course, this is not perfect. The key assumption here is that you know electricity prices 3 days in advance, which you don't, clearly. Right? There's no way you know them. You will know them for 24 hours, but you don't know them 3 days in advance. So what do we do? What we did was to switch to a moving horizon approach. So our approach was to say, well, we really don't know, and maybe we don't need to look that many days ahead. What we can do is make a decision today, update our information tomorrow, and shift our horizon up by 1 time unit, 1 day, and then keep going that way, right? So we can, on a moving horizon, we can keep making our decisions. So, but the question is, well, I don't know 3 days in advance either. I just know 1 day. So we have to say, let's be lazy. Right? Lazy is good. Lazy was the solution here. We said, well, what if we say, given that these prices are kind of periodic, what would you lose by just saying, well, what if today is like tomorrow? And the day after tomorrow is like today. And then tomorrow, I'm just going to say, well, I know the prices for today, but I'll assume the next 2 are the same. Or I could take the day from the week before. So today is Thursday, tomorrow is Friday. I'll take last Friday as my prediction and so on. So that way I can account for weekly changes. What would you lose? And not much, right? So here, with this strategy, the omniscient strategy, we know we can reduce prices by about 1% or operating expense by 1% over 6 days. Here, we're 0.8% down. So by applying this strategy, which assumes nothing in terms of predictions, we don't have a prediction mechanism. We just take the super lazy approach. We're still doing well. And why is this important? This is important because now you have to go convince practitioners. And the practitioner will say, well, I don't know how to forecast prices. Well, you don't have to. You can just do this. And of course, it's important to study this over a range of scenarios, right? One single experiment is worth nothing. So we, of course, went and did a lot of studies on scenario-based studies where we looked at the electricity prices and we said, well, the uncertainty in forecasting prices kind of increases as you move up in time. We solved this as a chance constraint problem. So this is a problem for optimization under uncertainty where you're saying, I will meet the condition of having a feasible solution for alpha% of our scenarios. So let's say 95%. And then how does this compare? So I'll present some results here. This is our base case with no schedule optimization. Then we look at knowing everything for 6 days in advance. Here's the chance constraint scenario. This is the moving horizon scenario for the first set of prices that I looked at. And you can see the difference here is quite stark, right? So this chance constraint solution is more of a conservative solution. It says, I need to have some probability or guaranteeing that I will make the product that I need to make at the rate I need to make it and so on. So generally what this means is that I use more storage. I store more material. So I'm just bulletproofing my solution. But if I look over 200 scenarios that we generated and compare the mean for the chance constraint and moving horizon approaches, they're ostensibly the same. So what this tells us is that this very lazy moving horizon approach is as good as a relatively sophisticated way of bulletproofing your solution against uncertainty. And not only that, it's economically very, very interesting. So the benefit of what I mentioned here is that the moving horizon approach can be updated with lots of other information, such as weather, which impacts the operation of a plant like this, can be updated with information about product demand and so on, whereas if you were to do this as an optimization under uncertainty context, the problem size would grow considerably. So this becomes advantageous as the complexity of the problem grows. So what's going on now? Well, we're actually doing this on a real plant that makes both oxygen, nitrogen, argon. We're doing it based on plant data, so now we no longer have a model, and we're going to try to do it just based on data collected from the plant. And we're dealing with essentially a very big data problem, looking at enough time windows to be able to get a decent model. So I guess stay tuned for those results. We have some initial publication, but there's more to come, and hopefully this year we'll have a field implementation. Right, so let me close the chapter on energy and start thinking about food. So food is obviously a big problem. There are statistics that I've seen from the FAO that said that malnutrition is a huge problem, food security is a huge issue, and the United Nations has some goals that are ambitious. We want to sustainably double agricultural output and end hunger and malnutrition. And again, the grandma question that I'm going to ask now is, do we have to, right? Do you have to buy a new car? Do you have to double production? I don't think we do. Also, the United Nations says 1/3 of the food that's produced for consumption is wasted, right? 1.3 billion tons a year. That's a huge amount. And this is, food loss is the drop in quality below acceptable levels from the suppliers, the manufacturer, through the supply chain. So it's natural to ask yourself a question: how can we prevent this terrible occurrence, essentially? And this doesn't look any way at our fridge, right, where there's a lot more food wastage. So what does the supply chain that we're dealing with look like? Right, we have producers, raw materials. This could be fertilizer, anything. So these guys would produce stuff, send it to warehouses, and then this gets distributed to retailers. So this would be Cub Foods, Rainbow back in the day when I was here, and then get to us. And you can imagine a banana going through this across borders, across countries, across shipment methods. It starts off green and it ends up black. And we know these make the best banana bread, but they're not the most appealing to buy. And the question is, well, how long does this take? Well, it doesn't take that long. It takes about as long as the transition time through this entire supply chain. So this is what defines what we call a perishable product. The perishable product is something that has a relatively quick degradation rate compared to its transition from producer to consumer. And you can see here that we have quality. So if I don't define quality specifically now, but you can imagine that we start somewhere here, and then this quality will eventually degrade below some threshold that defines the usability of that product. So how do we model product quality? We'll call it Q. So we write the differential equation that gives us some time dependence. And this quality is a function of itself in a sense. It's also a function of environmental conditions. So this could be temperature, for example, for storage. It could be the presence of ethylene, which is used for ripening. There are other conditions, humidity, for example. So all these could be part of this model. Now, quality, you have to imagine, think practically, think mathematically. Quality is bounded, right? There's an upper bound of how good a piece of fruit can be, and there's obviously a lower bound beyond which you're not going to eat it. Right? So there's a min and a max on quality. And this function, we can assume pretty safely that it's monotonic and that quality is monotonically decreasing. So the quality of a piece of fruit is not going to get better. It only gets worse over time. So what we need to do is, our task is to find these inputs over time during the passage of this product through the supply chain such that at the end point here, the quality is above some threshold such that it meets its minimum quality standard, but at the minimum cost. So that means we could vary the temperature, we could vary humidity, we can vary storage time, etc., before this product goes bad. And it's incredibly difficult to do because this becomes a multi-scale problem, right? The time scale of the supply chain planning activity is in the order of weeks or even months if you consider back orders and so on. Whereas the dynamics of the quality, how long does it take for a banana to go bad on your counter? A few days, right? So we're looking at a few days, and these time horizons kind of overlap. So we have to account for what those are. So at the supply chain level, it's very simple. Each node is modeled as an accumulator, a tank, if you will, which has an inflow and an outflow. So we do that. And then we integrate inventory balances or quality in this inventory balances by saying, I will assume that I'm quantizing quality levels. So there's only Q, and there's a delta Q at every time instant, and I'm indexing inventory levels over that. So what that means is that I keep track of inventory of every quality. So I'm saying I have an excellent banana, a level of excellent bananas, a level of mediocre bananas, a level of bad bananas, and then I know what the inventory of each is going to be. So with that, we can formulate this problem as kind of a input state output model that's written in what control, something that a control researcher would deal with or understand. So we've shown that this is possible, and we can write the system dynamics in this discrete time form. So we also impose some constraints. Here we have to do with how much inventory you can store in a warehouse, and then use our transshipment between nodes. So how much can you ship from one place to another? This can have to do with, let's say if you do it by train, how much can you fit in a rail car? If you do it by truck, how many trucks you have available, and so on. So the way we approach this problem, typically the way this is approached is one would plan production, shipment, storage, and so on over a whole time horizon. So let's say this would be about 3 weeks. What we propose to do is to break this down into a moving horizon problem, kind of akin to the scheduling problem that I presented before, where we call the control horizon is the amount of time that we take between decisions, and then prediction horizon is how far ahead we assume we can see in terms of product demand and product degradation. And this is much shorter than what the traditional problem would look like. And in the meantime, we take measurements of product quality from the product itself. So we formulate two problems here. The open loop problem is the traditional supply chain problem that you can find in the literature for this kind of products. So here you have a long time horizon, and the entire problem is formulated over this long time horizon, subject to some cost metric, and then also subject to the dynamics of the supply chain, which I described earlier. And you have some initial conditions, meaning what quality you start from, and the constraints that I mentioned before is storage constraints and transportation constraints. Right, this closed loop problem that I'm going to describe is the problem that is formulated over a shorter time horizon. And here, the difference is that we add another constraint such that at the end of the horizon, we are actually close to the solution of this larger problem. So let's look at an example. This has to do with bell peppers. So the degradation rates are, as a function of temperature, are taken from experiments that have to do with the bell pepper supply chain. We look at a simple network topology. So we have 2 producers and 4 consumers, let's say. So these could be 4 supermarkets or so. And here is some interesting assumptions we make. So this is the lead time, meaning how long it takes to get from one producer to one retail node. And you see here that starting from this guy, it takes 2 to 3 days, whereas this supplier can supply in 1 day. But the costs are quite different. So if you have enough foresight to order, you pay about 10% of the price of the just-in-time supplier. Right? Admittedly an extreme case, but not unrealistic. Right? So if you expect your stuff now, it's going to cost you. So the dynamics we model, the degradation of quality, we quantify it in some relative arbitrary unit, and it goes from 6 to 750. And the temperature, so this is a function of inverse temperature, and we again assume that there's some temperature levels that the warehouses and trucks can operate at. So this is degrees Celsius or Kelvin. So the question is, well, how do I plan, knowing how much demand I have at these nodes, how do I plan ahead? Where do I order stuff from such that the cost is minimized and spoilage is minimized as well? And it's interesting and instructive to sort of try to run these moving horizon problems assuming different horizon lengths. So this means control horizon length is how often do I recalculate the plan and how far in advance do I look. So the nominal problem is solved for 30 days. And here I'm saying if I only look like 2 days in advance or 2 weeks in advance, how much would I lose, right? So if it's plus, it means it's costing me more to do this moving horizon approach. And you can see that if I have a lot of prescience, so if I have 2 weeks of foresight and I can do this every day, the answer is not much, right? So I'm actually close to the nominal solution. If I only do this every 7 days and I only look 6 days in advance, the problem becomes infeasible. So that's not good. So somewhere here in the middle, we have a sweet spot, right? And you see that if let's say I rescheduled every 4 or replanned every 4 days and I look 2 weeks in advance, I'm not too far off. If I do it every 4 days but only look 6 days in advance, then I'm really far off. So the cost's almost double. But this is encouraging, right? It says that we can do this without much loss, and I will show there's actually a benefit to applying this strategy. So the benefit of applying this strategy is more obvious if we actually do a hybrid approach. So in this hybrid approach, what we will do is we take the solution of the main problem over 3 weeks and use it as a base case. So whatever we do over repeated decisions, receding horizon decisions, are just going to be a correction from this main problem. And the way this works is in the receding horizon problem, we add a regularization term or a penalty term that penalizes the objective of this, or the deviation of the deviation of the solution of this problem from the solution of the nominal problem. And we can adjust how much we weigh or bias towards the nominal problem by adjusting this parameter here. So it's illustrative to look at some case studies. One of them would be to look at the main planning problem for nominal demand and look at actual demand. So assuming the demand is constant is kind of the base case, but we also look at how demand can fluctuate over time. And you can expect that that's always going to be the case. We also look at the fact that we cannot perfectly model the degradation of produce. Produce comes from different sources. They're never going to be the same. So their behavior over time and their rotting behavior, if you will, is going to be different. So it's interesting to see here that the production levels between the usual formulation of receding horizon and this regularized problem is going to be very different. If we don't apply the correction, there's going to be these hiccups when we really have to place some rush orders for the expensive producer, and the cost is going to be very high. Whereas if we apply the regularization term, the production level for the cheap producer is going to be flat, and there's going to be some minor corrections from the expensive one. The same goes for transportation temperature. So here we have this nervousness and temperature, whereas with regularization, we get to the point where temperature is actually pretty well stabilized. In terms of total cost, we get to the point where by applying this lambda correction, the cost of our strategy is very close to the case that has perfect knowledge of the solution of all the disturbances. But the computational cost is significantly lower if you look at these cases. What's interesting here is if we take into account variability of demand. And obviously, we have to look at a lot of scenarios, which is what we did here. And demand standard deviation tells us how much demand fluctuates. And you see that this optimization under uncertainty approach, so when we account explicitly in a different formulation that's similar to the one I mentioned before, for uncertainty in demand, the solution becomes more and more conservative. So in our case, if we update the information, the cost is really oblivious to the fact that demand becomes more and more uncertain. But when we try to account for it explicitly, the costs go up quite a bit. And well, that takes us back to the United Nations problem, how much product gets spoiled. If we have this, let's say, cautious supply chain where we pre-order a lot in order to meet the demand of choosy consumers, you see here that the inventory wasted is many orders of magnitude higher than the inventory that would waste by applying our approach of ordering and updating the solution as more information comes in. So here, the optimization under uncertainty says, let's order as much as we can so we have enough inventory at different nodes, whereas here, we just order as much as we need. So with that, I think I need to bring up what's the latest and greatest here. We're working with our colleague in chemistry to come up with methods to actually measure product quality and quantify it, style or smell or color. We're developing a mass spec pen that, well, they've developed it already, but we're adapting it to measuring product quality and getting real-time measurements that can be then used to update these calculations. So hopefully, with some support from one of the bigger supermarket chains in Texas, we can implement some of this. So with that, I think it's time to close and draw some conclusions. I think what I tried to show today is that we are, as a race, as a planet, facing some big challenges. And I think that by thinking in the systems way and thinking orthogonally to the canon, to the current practice, we can come up with exciting solutions that are low cost and easy to implement and use existing infrastructure. So they don't require a whole lot of infrastructure development. Now, the fundamental notions that we developed here are the extension of concepts from model predictive control, which is an established theory and approach in the control of chemical plants, to much larger systems that can be spanning multiple lengths and time scales. Fundamentally, we argue that we can use feedback to counter uncertainty. So updating information is oftentimes better than preparing for the unknown. And we do have extensive studies at the theoretical level of the stability of these approaches. We've compared them also extensively with established approaches for optimization under uncertainty, and I think the results are very, very favorable. So I really need to acknowledge a long list of students and collaborators that have contributed to this work over the years. I've been privileged to work with all of them. I'm also thankful for the support that we received from the NSF and the Department of Energy and industry sponsors who came with challenges, real challenges to us, and constantly challenged them to address them. And I'd like to thank you for your attention, and I'd be happy to take any questions.